hear you.
Hey!
Hey!
Quiet. Dalton. Let's get back to Dalton.
Dolphin.
Hey, first review. Eusebius and Democritus. They were what?
Greeks.
They were Greeks. What didn't they do?
Experiment.
They didn't experiment. What did they do?
Set up their bums and think.
They kind of just thought, right? Which guy is kind of credited for coming up with the term atom? Even though it was really Eusebius that kind of started the whole process. Okay? Now, Democritus tried to take what Eusebius said and started to like, oh, how do these atoms interact? And he put fish hooks on them, remember that? Okay, Dalton created his first experimental model. What he did is he started weighing a whole bunch of substances based on a law of definite proportions. Here's what the law of definite proportions is. Law of definite proportions says that for every H2O molecule, the mass of hydrogen and the mass of oxygen within that water molecule is always the same ratio. Here's what I mean. I'm going to try to use whole numbers so this kind of makes sense. If I have 9 grams of H2O, hydrogen will be 1 gram of it, and oxygen will be 8 grams of it. If I have 18 grams, hydrogen will be 2 grams of it, and oxygen will be 16 grams of it. Still the same ratio? What is the ratio between oxygen and hydrogen? 1 to 8. Well, 8 to 1 if you say oxygen to hydrogen, right? Okay, if I had 27 grams, you get the picture here, 3 grams and how many? 24 grams. Does 3 and 24 give you 27 total? Is it still an 8 to 1 ratio?
Yeah.
Okay, so what he did is he did this with a whole bunch of common, well-known compounds like CO2 and many other things. And he noticed, using this, that he could determine kind of, did you just do that?
He was better than organization.
So what he noticed was he started comparing relative masses, is what he did. And what's really kind of interesting is he said, based on doing all of this stuff with multiple things, he said, hydrogen is really, really, really small in comparison to oxygen. And yes, it is. It's quite a bit smaller. But he said, oxygen is only a little bit more massive than carbon, which he was right. Now, did he know the exact masses of each of them? No, but he figured out relative to each other. So carbon is not quite as massive as oxygen, oxygen is not quite as massive as neon, and he started making all these relative concepts, relative distinctions with each other, which was kind of a big deal. Now what he thought is that he thought oxygen's mass was 8 and hydrogen's mass was 1. Hydrogen's mass is 1, but oxygen's mass is actually 16, because he did not know that a water molecule has 2 hydrogens for every 1 oxygen. So it was 2 hydrogens that made up this amount. So really you can say hydrogen would be 0.5 to 8, which would be a 1 to 16 relationship, which is what it is. Hydrogen's 1, oxygen's 16. Okay, and he didn't know that, but he was able to figure out some pretty cool distinctions. Okay, and the law of definite proportions, which is what he was using when he noticed that there was always the same ratio by mass, was discovered by a guy by the name of Joseph Proust, which simply states that every compound has a definite composition by mass. Same set ratio, same amount of stuff every single time. Now we know that, it makes sense now, but at that time it was a pretty big deal. Did you guys get all this in?
Yeah.
Okay. Did you get this in?
No.
This is what I was stating earlier. He noticed a 1 to 8 ratio by mass. But remember, he assumed that there was only 1 hydrogen and 1 oxygen for every water molecule. Excuse me. As soon as we get this and I'm moving on because I've already talked about it. Got it? All right. Here is Dalton's model, what it's called.
Ew. Clarinet. Trying to play. Whoa.
So now, Dalton this is really important for you guys to make note of, is that Dalton is the first guy to actually do experimental evidence. Greeks did no experimentation. Dalton, very much, when he started breaking down water molecules and many other compounds using the law of definite proportions. Okay, he came up with a core envelope model, and his model still isn't like that much better than the other guys. And since his model and the work that he did was so much involved around figuring out the masses of things, you're going to see his model has a lot to do with this. He believed that each atom was the same size, but the difference in mass was the result of these like heat bubbles around them, if you will. He called them heat envelopes. I don't know why they call them envelopes, maybe because they completely surround it, I don't know. But he basically said that the difference between the mass of a hydrogen and the mass of, let's say, an oxygen is that oxygen has a bigger heat envelope. A heat bubble, if you want to call it that. So there is your little visual of Dalton's model, if you want to make note of that for your note cards. All right? Here's what he came up with. He actually came up with some pretty important stuff. He said that atoms can either be created or destroyed, and that is absolutely correct. I'm trying to think, I don't really know. I'm assuming this came before we actually came up with the first law of thermodynamics, which states matter and energy cannot be created or destroyed. What up there is not true? Atoms can't be subdivided. If you looked at his model, right, his core envelope model, looks like one solid sphere still, doesn't it? So his model just looks like a solid sphere with a heat envelope bubble. Still, have we found the electron, proton, or neutron, or nucleus, or any of that stuff yet? Or have we gotten there?
No.
No, we're still got a ways to go. We're going to get there today, or at least start getting there when we start talking about the next couple guys. Okay? A couple of things about his model. C is right, but believe it or not, D is not correct. I would be really shocked if you knew why, but I want to open it up to see if anybody has any ideas as to why D is not correct. Yeah? I don't expect any of you guys to be able to answer this, but I'm just curious if maybe, previous school or somehow you did something or watched a YouTube video or something. Have you ever heard the word isotope?
Yeah.
Okay. We're going to talk much about isotopes later. What an isotope is each of these individual atoms up here, so like magnesium, okay? All magnesium atoms have 12 protons. All magnesium atoms have 12 electrons. But not all magnesium atoms have the same number of neutrons. And so since they have different numbers of neutrons, or have the ability to have different number of neutrons, can you say that all of the atoms of a particular magnesium element are exactly the same? No. Okay, we'll talk about isotopes. I think it's in this chapter. Later in this chapter, we'll talk about isotopes and a few other things. So, but just note that that was something that up front probably made a lot of sense to him, but hadn't discovered isotopes. Oopsies.
Wait, that's it.
For yesterday's lesson. And he was right about this. Atoms of elements differ in their masses. So he has kind of figured out some stuff that is very valuable, but we got some work to do? Yeah. Got some work to do. Next guy, before we get to the next guy, I want Ethan to get this in.
Other people didn't get it.
I think you were the only one. Just problem 5 and 6, Ethan. No big deal. Got it? Wait, the whole time you wrote it on that?
No, I just writing that down. So now I'm gonna write
We
it
should have
down.
done that. All right, Mr. J.J. Thompson is our next guy. And I don't remember if you guys all put these in at the very beginning or what you guys were doing on this, but I do not want you to rewrite all of these guys every single time again. Does that make sense?
Yeah.
Just waste our time. All right? So, here we go. J.J. Thompson, here is what he discovered. Whoopsies, go back. He was, and I'm not going to get into his experiment and how he discovered it. If you take chemistry, we talked pretty lengthily about his experiment, what he did, and what led him to discover the electron. I don't think we're quite at a place yet where we're ready to kind of go deep enough. Get this one up. All right, so what did he discover? The electron. Okay, tell me what you know about electrons. They're negatively charged, okay? What else? Outside the atom, okay, orbiting in what we would call an orbital or electron cloud. We'll get to that later. Anything else you know about electron? Relative size, you know relatively how big it is in comparison to like the proton or the neutron. You guys remember? We talked about it. Been a while. Been like a week. Okay, been like 3 weeks. Electron is the smallest of the 3 subatomic particles. Quite a bit smaller than the proton and the neutron. All right. So again, I'm not going to go into how he discovered the electron because that will be a little more advanced and for a higher level. Okay, so here's what his model was. I'll have you put this in, and then I'm going to talk about how he came up with his model based on his discovery of the electron. last year. Of what slide? This whole day or this slide here? Really? Where? In school. Oh. Sweet. Good thing we're gonna go over it again then. Cool. We're still pretty early on in chemistry. It's gonna get more difficult. But yeah, we're just kind of building the foundation. Can't really talk about compounds until we know how the atom works. Can't really write chemical equations until we know how compounds work and how to write compounds and how to balance compounds and things like that. Can't balance equations until we know all of that. So, we got a ways to go. A lot to learn this year. Maybe. Do you remember the stuff from the previous? Do you remember all the sig fig stuff? And yeah? Kinda? You know how to balance a chemical equation? Okay, then you. Alright, so here's what he did. So he discovered these electrons, right? So let's say he discovered these electrons and he knew that an atom had these negatively charged particles in them. Okay, here's what he couldn't rationalize. He couldn't rationalize how the atom was neutral. Right, because up to this point, he was able to discover that there were negative things in the atom, but overall, the atom was neutral. He knew that. When you take an atom, you put it up to a magnet or an electrical field, it doesn't do anything. Okay? So he said, it's got negative things in it, but overall it's neutral, so what does it probably have to have in it? Something positive. Now, he hadn't discovered the protons, but his model had to somehow show that the overall atom was neutral. And how he did it is he said that really these negative electrons were really in, where is my pencil pen? Yeah. Got it. Okay? He said these negative electrons were embedded in a positively charged mass. And his model was called the plum pudding model, or if you're American and not like overseas, I don't remember what country he was from, but I guess plum pudding was like something that they ate a ton.
Sounds delicious.
Plum pudding, I think, is like pudding with raisins in it, or plums. Sounds awful.
Can we mark something?
You want to make plum pudding?
No, I don't want to make it. I'll make it.
Look it up.
Change the food guy for the
I'm pretty sure it's awful tasting, I'm guessing.
Yeah.
Doesn't sound very appealing. I like to call this, you're probably more familiar with this in America. How about the chocolate chip muffin model?
Well, what?
Now, what do you think the chocolate chips in the muffin represent? The electrons. What do you think the muffin represents? The positively charged mass. Okay? So, it still kind of looks like a sphere, doesn't it? But it's just got these embedded negative things in it, yes?
I just got stuck in my acrylics now.
Yeah. Eyewash right there.
Where? How do you, we want to see how you use it. Does it screw your eye? Oh, what the?
You want to wash your eyes out? There you go.
That's so weird. Shit.
It's like in the corner of my eye.
Why do you have that?
Just in case I squirt chemicals in someone's eye on accident.
That sounds great.
That help?
Yeah. Yeah, I can see that.
Hey! Perfect. First time I've used that. Because I try not to squirt chemicals in your eyes.
I would use it.
Alright, so this is what, again, probably a better version of what I drew up there. Remember, he's got your spherical atom, okay, your positively charged mass, which if we were talking about a chocolate chip muffin example, would be like your dough or your batter or whatever you want to call it. And then your negatively charged electrons inside of it would be represented by like your chopped chips. Yeah?
Yeah.
Yeah. Ouch.
What's your marshmallows and your hot chocolate?
Ugh, my knee hurts. Yeah, regarding Issa, and Issa is going to get a lot of offensive fouls this year. And he comes just bam, knee right here. Ouch. Probably bruised. But he didn't score.
Wait, you go to East and didn't score?
I'm the only one who can guard Issa of everybody.
What's Steven Brisbane?
No. Most people are afraid of Issa. I am not. That's honestly what frustrates me about a lot of like high school kids. Are like, oh, I'm so intimidated by this guy. How about you just suck it up, play hard, and shut him down? Wow, not that hard to do. Anyway, sorry. Didn't mean to say that. Not really that
It's
important.
on the camera.
It is on the camera. No, Lisa and I have good little battles.
Quick, show the footage.
All right. Thompson.
Club pudding. A hot
Looks like a hot dog. Good kid. That was a real hard question.
No, I-
Thompson's cathode ray. Okay, so I'm not gonna talk. I wasn't gonna talk about it, but his experiment was called the cathode ray experiment. Essentially, what he did in a nutshell is he put a really, really high voltage onto a metal cathode, and he noticed a beam that shot off, and that beam was negatively charged, which led him to believe that there were negative electrons inside the atom. Okay, so the cathode ray was the what, do you think?
Electrons.
Yeah. Okay. All right, last guy for today, Mr. Ernest Rutherford. Rutherford. Don't you wish, Annie, you could just go back to this? No, you don't wish that. You like being smart. Alright, moving on. Okay, so we're progressing. We found the negatively charged electrons. Here's some background as to what he kind of discovered. I'll have to get this in and we'll talk about him. And we will talk about his experiment a little bit more than we did J.J. Thompson's. Yes, sir.
In the homework, you said 261.
Oopsies. Were you on 161?
I don't know, 261.
Oh, it's 361?
Yeah. Okay.
Brett Garland. You can do it.
What?
Hey, Clifford.
I always did.
Yeah,
I did. I did like every single time.
All right, let's talk about this. Okay, based on what she just read up here, I know I haven't talked about it. What did he discover?
there's protons.
Actually, I know it's kind of a little eluding. What he really discovered was the nucleus. And it actually wasn't until a little bit later that the protons were discovered. Okay, he actually, I think, later on did discover the protons, but with his first experiment, he only discovered the nucleus. Here's in a nutshell what his first experiment was. Okay, I know this is probably going to look pretty confusing. Don't put this in, okay? But what he did is he shot alpha particles. And if you look at the last line, what alpha particles are is they're just really, really, really small positively charged particles. Okay? Think of it as a bunch of protons. Now, it's not quite that, but it might be the best way for you guys to understand it. Okay? Yes?
What don't make sense to me is how all these people are shooting and throwing particles everywhere.
Yeah, you gotta know what you're doing. Yeah, it's not just, okay, I'm just gonna shoot particles where I want. It's not quite how that works. But yeah, usually it has to do with having nuclear type of stuff. But anyways, so what he did is he actually shot really, really small particles at gold foil, and what he assumed would happen is that the particles would shoot right through the atoms, because he's kind of assuming at this point that plum pudding model is the real deal, right? Okay? He kind of expected those particles to kind of just burst right through the plum pudding model and get detected by a detector on the opposite side. Okay, believe it or not, if I were to shoot alpha particles at this desk, most of the alpha particles would go straight through it. It's kind of weird to think about, huh? You guys know at a subatomic level, even this is mostly open space. Like if I was a subatomic particle, I could just go right through that desk. Mind blown, right? I know, that's all, even now that's kind of hard for me to realize, but at a subatomic level, right, we know there's a nucleus, and then we know there's electrons on the outside, right? Well, what's all in between the electrons and the nucleus?
Nothing.
Open space. Okay? And so what he did is he shot these alpha particles at this gold foil, and most of them did go straight through. But what he noticed is that some of the alpha particles appeared to be hitting something inside the atom and ricocheting at an angle. What do you think they were hitting? The nucleus. So a bunch of particles were going through, and most of them were going straight through. Some of them were hitting the tiny nucleus and ricocheting. But remember, comparatively, the nucleus is really small comparative to the whole volume of the atom, because most of the atom is really just empty what? Space where the electrons are in. So at a subatomic level, even this desk is mostly open space. Isn't that kind of crazy? That's crazy. Kind of see through there. No, I mean, right? That was just an absolutely crazy discovery to realize, wow, it's really just open space. So his model is called the nuclear model. And I think there's an actual visual of the nuclear model. If not, I'll write it on the board. And the reason it's called the nuclear model is because he discovered the what? Nucleus. And again, it wasn't until later that he discovered, let me see how much more. Oh, one more after this and it's just your model. Nice. We will get done on time! Woohoo! What?
Go back to
Leave a space and you can get it after class. Or you can ask somebody what it was. Because I want to make sure we get all the notes. So you can do your 2 problems of homework.
Oh no!
What? So much. And notice, look at this. Look at how small the nucleus is compared to the rest of the atom, which is mostly open space.
What would happen if there was no open space? Like if there's a block, but there's no open space in
then nothing would be able to get through.
It's super specific.
Yeah, but there's nothing that's like that. Like if you could stack all the nucleuses next to each other of atoms, then maybe, but not possible.
Would you like to principle?
Probably. I mean, we're talking about a bunch of positively charged nucleuses that would just repel each other.
It's like putting backwards some giant piles and go.
Well, they would probably just orient themselves so that they
Yeah.
interacted, and unless you could just take. Do you guys know that if you were to take a magnet and cut it in half, it just creates two different magnets? It doesn't create like a positive magnet and a negative magnet.
Really?
Yeah. Kind of neat. Alright, so here's where you can kind of see that the electrons are much smaller than the protons. Okay, we could probably say, we'll go ahead and say that Rutherford, his main discovery was the nucleus, but later he did discover the protons. Alright, because obviously this appears to be saying more about the protons than I think it should. And so this is just kind of telling you what his model looks like, and then on the next slide we should grab, before we leave, the actual model, what it looks like. Okay? Everett, you still writing this one? How much more you got? I do want to give you the model of the atom so that we can get it all done. How about those who are first shall be last?
Oh, Bible smackdown.
Oh, there's one more. Oh, that's an important one. Oh,